2.1a is identifying location in a distribution. We're talking about percentiles and z-scores. So let's start with some vocabulary. The p percentile of a distribution is the value with p% of the observations. And I'm going to change this a little bit. It should say at or below it. So let's look at our example. If Jenny is in a class of 25 students and makes an 86 on her test, she has the fourth highest score. Is her percentile the same as her percent correct? So fourth highest score out of 20 students, or 25 students. So let's see, what would that look like? Fourth highest, that would be, so we have the highest, the next highest, the next, the next. So she would be student 25. So she is at 25 or above. So we do 22 out of 25, which is 0.88. And that is the 88th percentile. So what this means is Jenny's score was higher than 88% of students who also took the test. So she is the 88th percentile. So she made an 86, but her percentile is 88th. So those are not the same. So the answer is not the same. Okay, example, wins in Major League Baseball. The stem plot shows the number of wins for each of the 30 Major League Baseball teams in 2009. Calculate and interpret the percentiles for Colorado Rockies, who had 92 wins, Yankees, who had 103 wins, and Cleveland Indians, who had 65. So I'm going to underline the important information. Okay, so the Rockies had 92. So let's find out where 92 is. 92 would be right there. And so there are 30. So 1, 2, 3, 4, 5. So this would be 25 out of 30. Because I could count it the other way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So that's how I got it. But I went the opposite way and just took 30 and did 1, 2, 3, 4, 5, 30 minus 5. So that is 0.83. So the Rockies are an 83rd percentile. Okay, the Yankees was 103. So 103 is right here. So it was higher. It was at or higher than 30 out of 30. So that's 100%. So it's 100th percentile. It's the highest. The Indians, it says it's 65. I'll do a different color. So where's 65? It's here at or below. So 1, 2, 3, 4. 1, 2, 3, 4. Oh, 5. We're going to go 5 because these are the same, at or below. So at the other 5, I'm still at 5. So I'm going to go 5 out of 30. 0.17, which is the 17th percentile. Okay, we are going to look at a different type of graph. So this graph is called a cumulative relative frequency graph. So not much room to write this. Here is a cumulative relative frequency graph, or ogive. And you say it sounds like this. Okay, so cumulative means when you add up all of those values from one to the next to the next. So it's going to keep on getting larger. Relative is percents. Relative frequency would be percents in relation to each other. So this graph is going to show the distribution of median household incomes for 50 states in the District of Columbia. So we have, 50 states and district, so all the states. So this says California with a median household income of 57,445 is what percentile? Interpret this value. So let's look at median household income. Let's go to 57. So this would be 57 and a half. So it'd be a little below. So I'm going to straight up. So it's right here. So let's see what percentile, what relative percentile would that be? So looks like 80th, a little bit below maybe. But I'm not sure if my line went above or below. It's hard to tell on the iPad. Looks like, okay, it's about right. So we'll say that this would be 70.70. So that would be 75, so a little bit above, maybe 78. So it is the 78th percentile. And it also says interpret this value. So we actually need to interpret this value. So I need to write it in sentence. You know what? I might type it. The median household income of is at approximately 78th percentile. Let's go back. There should be 7. Okay. And what does this mean? This means that in California, the values or the household income is higher in California than 80% of the other states. So it has a higher. Let's see. There we go. Is at approximately 78th percentile, which means the household income in, see if I can add to that, which means the household income in California is higher than 78% of the other states. Okay, so that should all be one sentence. Okay, let's go to the next one. What is the 25th percentile for this distribution? So let's see. I'm going to use a different color. So I'm going to go to 25th. So this is 30. This is 0.3. So this would have to be, so it looks like 45,000. And then what is another name for this value? I'm just going to write this one. The 25th percentile is approximately $45,000, which is also called the first quartile, or Q1. Okay, let's keep on going. Where is the graph the steepest? So it looks like, I think, looks like from here to here. This is going to be like the box in the box plot. I wonder if I should go ahead and include this. I think I should, because this is also steep. So let's go ahead and include all of that. This is very similar. So the steepest part of the ogive is from about 40,000 to 55,000. I'm going to put a K there. Representing, then we also need to talk about what percentile that is. Between, let's see, between 5% to 70% of the data. The remaining, what if I kind of went down? So maybe 75 actually. I want it to be. Okay, so between 5 and 75, so that's about 70% of the data. So the remaining 30%, or 25, because I'm just going to talk about the right tail. The remaining 25% is to the right tail, creating a slightly skewed graph. So it'd be the tail on the right, so it'd be slightly, I'm going to go ahead and add in there, right, skewed right graph. Okay, so an ogive that is skewed right looks like that one, where you have your, let's go like this, where it's slow, steep, and then like that, let's say. And so then if we have a skewed left, it's going to look like this. So it's kind of reverse. And then symmetric, it'll look the same on both sides. So look, this, this, this. So it looks very symmetrical, where you have your steepness right in the middle, and then it's the same on both sides. Okay, let's move on. Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy. But who is taller, relatively speaking? This is relative to other kids the same age, who is taller. According to the CDC, the heights of 3-year-old females have a mean, so the girls will have a mean of 94.5 centimeters, standard deviation of 4. And then boys, same age, that 12, is 149 centimeters with standard deviation of 8. So we want to see how we can compare these. So one way is just to look at how it compares to the mean. So she's 100 centimeters. The mean is 94.5. So she has 5.5 centimeters above average girl, same age. And then we got Brody. Brody is 158 centimeters compared to, let me fix that, 149. So that's 9 centimeters above average. Boy, same age. So that's kind of hard to compare. We're not going apples to apples. We're doing boys, girls, and a particular age. So what we're going to do is consider the typical deviation from the mean. So we'll look at Macy. So she is 5.5 above the average girl. What's our standard deviation? 4. So we're going to see how that compares. So I divide it, 1.375 standard deviations above mean for girls only. Okay, and then Brody, I forgot my R, is going to be, his was 9, but the standard deviation is 8, 1.125 standard deviations above the mean. So who would be considered taller for their age? It would have to be Macy, because she is taller than the typical deviation. So let's answer the question. It says, who is taller, relatively speaking? So Macy is relatively taller since she is 1.375 SD from the mean, while Brody is 1.125, and it should be centimeters because whenever you do standard deviation, you use the same units. Centimeter standard deviation. Standard deviation from the mean. Okay, so what we just found is our Z-score. So the Z-score tells us how many standard deviations from the mean an observation falls. So actually I should not have centimeters on Z-score. I really should just say 1.375 standard deviations and 1.125 standard deviations. And so my Z-score will not have units. So the Z-score tells us how many standard deviations from the mean an observation falls and the direction. So these are both positive, so they're above. If they were negative, they would be below. So Z-score is found by doing our given data, so xi minus the mean x bar over the standard deviation. So that's our formula, but in easier way, we're going to say observation minus mean over our standard deviation. So if we have positive Z-score, it's above the mean. If we have a negative Z-score, it's going to be below the mean. Okay, let's look at the next page. Go ahead and read that. Okay, so we are looking at baseball players who have just been pretty amazing. There's just kind of our world record home runs. So we have different players, we have different years, but we need to do is compare them. So our homeroom is going to be our XI, and then we have our mean, then we have our standard deviation. So let's go ahead and label our table. So we need to find each Z-score, so the standardized score, so that'd be your Z-score for each, and then we need to compare. So let's do Babe Ruth. So 60 minus 7.2 over 9.7. So we put that into the calculator. Get 5.44. Roger Morris. 61 minus 18.8 over 13.4. Let me divide that. McGuire. 70 minus 20.7 over 12.7. 3.88. So far, Babe Ruth has been way higher. Barry Bonds. We divide that. 3.91. So Babe Ruth definitely is the home run champ. So we do need to compare. So what is the same about all of them? Comparing our homeroom with our mean, they're all higher. So all players are above the mean for their respective years. Respective years. However, Babe Ruth is the home run champion, relatively speaking. So he was making 60 home runs, while the mean of the players that year in 1927, they were only making 7.2 home runs. So that is pretty amazing. Okay, last question. In 2001, Arizona Diamondback Mark Grace's home run total had a standardized score of Z equals negative 0.48. Interpret this value and calculate the number of home runs he hit. So instead of knowing what he hit, we have to go the opposite way. So we've got to know what this actually means. So Grace hit 0.48 standard deviations below the mean. Of, let's see, 2001. Oh, I need to go to Barry Bonds. The mean is this 21.4 home runs in 2001. So, see how it says below because it's negative. So we've got to figure out how many home runs they hit or he hit. So Z equals, I'm just going to use my formula and plug in what we do know. We know that the standard deviation or the Z-score for Grace is negative 0.48. We don't know what he hit, but we know what the mean was, and we know what the standard deviation is. That was from the above. Here's the standard deviation, 13.2. So we would need to solve this. So this is algebraic. Multiply by the denominator. And then add 21.4. We get approximately 15. So Grace hit approximately 15 home runs in 2001. That's still a lot of home runs. So even though the standard deviation, the Z-score is negative, he still hit quite a few. Okay, that is it for these notes.